The solar system is a small corner of the universe full of extraordinary wonders. It is the only place in the cosmos that, for now, we know has life. In it, the planets dance around the sun in an ancient, cosmic choreography. There are gigantic volcanoes, canyons of colossal heights, a place where the moons hide underground oceans, and where Saturn's rings weave patterns that defy the imagination. In this documentary, we will show what the solar system is like and investigate the reasons that make this place an oasis of uniqueness in the vast ocean of space. The formation of the solar system is a process that spanned millions of years, beginning with the collision and fusion of particles in the vacuum of the universe. At the heart of this cosmic odyssey is the protosolar nebula, a gigantic cloud of interstellar gas and dust. Within this cloud, the laws of physics played a crucial role, with gravity slowly pulling particles toward each other, increasing their density and temperature in the process. This phenomenon, known as gravitational collapse, was the first step toward the creation of our solar system. As the nebula contracted, it began to spin more rapidly, flattening into a rotating disk, the protoplanetary disk. In the center of this disk, where mass concentration and temperature reached their maximum, the Sun was born. This process of star formation, called accretion, led to nuclear fusion in the core of the Sun, releasing an immense amount of energy and marking the birth of our star. Meanwhile, in the colder, more distant regions of the protoplanetary disk, planets began to form. Small particles of ice and rock, known as planetesimals, were held together by the force of gravity, gradually growing in size. These planetary embryos, or protoplanets, continued their accretion process, attracting more matter and increasing their mass. The planets closest to the Sun, called terrestrial planets, were formed from materials capable of withstanding the high temperatures of this region of the solar system. Mercury, Venus, Earth, and Mars are examples of these rocky worlds, characterized by their dense atmospheres and solid surfaces. Beyond the orbit of Mars, in the coldest regions of the solar system, gas and ice giants formed. Jupiter, Saturn, Uranus, and Neptune grew to enormous sizes, capturing large amounts of gas and ice with their strong gravitational fields. These planets are distinguished by their large atmospheres of hydrogen and helium, and by the presence of rings and numerous moons. In addition to the planets, there are a variety of other celestial bodies in the solar system, such as asteroids, comets, and meteoroids. Asteroids, primarily located in the asteroid belt between Mars and Jupiter, are rocky remnants of the formation of the solar system. Comets, on the other hand, are icy visitors that come from the most distant regions, carrying with them valuable information about the primordial conditions of the solar system. The Sun, the source of life, is much more than a simple lighthouse in the sky. It is the beating heart of our solar system, a star around which all the planets revolve, including our home, Earth. When observing the Sun, what we see is the photosphere, a bright layer that emits light and heat into immense space. But what is not visible to the naked eye is the frenetic activity that occurs inside. The Sun is a gigantic sphere of hot gas, composed primarily of hydrogen and helium, where nuclear fusion reactions take place that release enormous amounts of energy. This energy not only illuminates our days, but also warms our planet, thus allowing life to exist. The solar energy that bathes the Earth is essential for numerous natural processes. Plants, through photosynthesis, capture sunlight, converting it into chemical energy that feeds the chain of life. It is a crucial process for plant growth and also produces the oxygen we breathe, thus showing the intrinsic connection between the sun and life on Earth. In addition, solar heat regulates the climate of our planet. Heating and cooling patterns influenced by solar radiation determine the various climates and meteorological conditions. These conditions affect the distribution of life on Earth, from microorganisms in the oceans to humans, demonstrating the omnipresent influence of the sun. But the sun also presents challenges. Solar flares and coronal mass ejections, phenomena associated with the sun's magnetic activity, can launch energetic particles toward Earth. Although our atmosphere and magnetic field protect us from most of these particles, extreme solar events can affect our communications networks and electrical systems. This makes us see the powerful influence of the sun on technology and, therefore, on our daily lives. Interestingly, the solar cycle, a period of approximately 11 years during which solar activity varies, influences the dynamics of our space weather and possibly Earth's climate. This cycle affects the number of sunspots and the intensity of solar radiation that reaches Earth, influencing weather patterns and auroras, those dazzling displays of light in the polar skies. Sunlight, when it falls on the Earth's surface, determines the rhythm of the days and nights. Likewise, it marks the passage of the seasons, influencing the growth cycles of plants and the migratory patterns of animals. In the history of humanity, the sun has occupied a prominent place in cultures and religions, symbolizing life, strength, and renewal. Its daily appearance is a constant reminder of the regularity and order in the universe, inspiring myths, rituals, and calendars that have structured entire societies. Mercury, named after the agile messenger of the gods in Roman mythology, is a world of extremes and contrasts. Despite being the smallest planet in the solar system since the reclassification of Pluto, its presence near the Sun gives it unique properties. Mercury orbits the Sun at a much shorter distance than Earth, completing one revolution in just 88 Earth days. This proximity to the Sun gives it the title of having the most extreme temperatures in the planetary solar system. During the day, its surface can reach 430 degrees Celsius, hot enough to melt lead. By contrast, without a significant atmosphere to retain heat, Mercury nights see temperatures drop to minus 180 degrees Celsius. This thermal disparity is unparalleled in the rest of the celestial bodies that we know of. Marked by countless craters, the result of collisions with comets and asteroids over millennia, this planet shows us a face that has remained unchanged for eons. Among its most notable geographical features is Caloris Planitia, a gigantic impact basin that evidences the violent youth of the solar system. In addition, Mercury hosts giant scarps, a product of the planet's contraction as it cooled and solidified. Another peculiarity of Mercury is its orbital eccentricity, the most pronounced of all the planets in the solar system. This eccentricity causes significant variations in its distance from the Sun, and therefore in the intensity of the sunlight it receives. This factor, combined with its slow rotation on its axis, each Mercury day is equivalent to 59 Earth days, contributes to its thermal extremes. Despite its apparent hostility, Mercury hides secrets that could redefine our understanding of the early solar system. Recent data suggests the presence of ice in the craters permanently shadowed near their poles, a surprising finding on a planet so close to the Sun. Exploration of Mercury has been limited, in part because of the technical challenges of sending missions to its proximity to the Sun. However, missions like NASA's Messenger and the upcoming Bepi-Colombo mission, a collaboration between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, are unraveling the mysteries of this elusive planet. Venus, Earth's infernal twin, is the second planet from the Sun and shines a brilliant light in our sky, often visible at dawn or dusk, earning it the name morning star or evening star. Beyond its distant beauty and proximity to our own world, Venus is an enigma wrapped in layers of mystery. Upon observing it, one finds a planet almost the same size and composition as Earth, which initially suggests a brotherly resemblance. But this resemblance is superficial, since Venus hides under its cloudy mantle a much more hostile reality. Its atmosphere is essentially composed of carbon dioxide, with clouds of sulfuric acid covering a world of extreme temperatures and crushing pressures. The greenhouse effect on Venus shows the potential excesses of this climate phenomenon. Carbon dioxide traps heat so efficiently that temperatures on the surface of Venus exceed 470 degrees Celsius. This dense, suffocating atmosphere creates a surface pressure more than 90 times that of Earth, equivalent to the pressure found in the ocean depths of our planet. Unlike Earth, where the water cycle helps regulate temperature and supports life, Venus lacks liquid water on its surface. Research suggests it may have had oceans in its distant past, but any water present evaporated and was lost to space due to intense volcanic activity and the runaway greenhouse effect. The surface of Venus, although hidden from view by its dense clouds, has been revealed through radar missions as a landscape of dramatic contrasts. Mountains, valleys, vast plains, and enormous volcanoes adorn this scorching world. The volcanoes, some of which may still be active, suggest a geologically young and dynamic planet. This volcanic activity, along with the lack of plate tectonics, paints a picture of a world in constant surface renewal, where geological features are endlessly formed and reconfigured. Venus's rotation adds another layer to its mystery. The planet rotates on its axis in the opposite direction to most planets in the solar system, a phenomenon known as retrograde rotation. Furthermore, its rotation is extremely slow, with a Venusian day lasting longer than a Venusian year. That is, the time it takes to complete one full rotation is longer than the time it takes to orbit the Sun. This peculiarity contributes to its extreme environment, allowing temperatures to rise to unimaginable levels. Earth, an oasis in space, stands as a beacon of biodiversity and complexity in the apparent void of the cosmos. This blue planet, with its rolling seas, vast lands, and atmosphere, is proof of the resilience and diversity of life. It houses everything from the tiniest organisms in the ocean depths to the majestic sequoias that rise into the sky. What makes Earth unique in the solar system is its ability to support life, something that has so far not been replicated anywhere else we know of. From the microbes that inhabit thermal geysers to the whales that sail the oceans, life has found a way to flourish in almost every corner of the planet. Every organism, from the smallest to the largest, plays a role in maintaining ecosystems, contributing to the cycles of water, carbon, and other essential nutrients. Earth's delicate ecological balances are the result of billions of years of evolution. Ecosystems, from coral reefs to rainforests, have developed in an intricate web of relationships between species, where the extinction of one can affect many others. These systems provide essential services for humans, such as clean air, clean water, food, and medicine. One of the most notable aspects of the Earth is its ability to maintain liquid water, an element crucial for life. The oceans, which cover more than 70% of the Earth's surface, are the habitat of rich marine biodiversity and regulate the global climate. They act as a huge thermal regulator, absorbing and distributing heat around the globe, and are a key piece in the water cycle, which supports life on land. Earth's climate is another factor that contributes to its uniqueness. The tilt of the Earth's axis creates the seasons, which in turn influence the patterns of plant and animal life, from plant flowering to animal migrations. This seasonal rhythm has shaped the evolution of species and human civilizations, which have sown and harvested in harmony with the cycles of nature. However, the Earth is also a planet of change, where natural phenomena such as earthquakes, volcanoes, and storms have the power to reshape landscapes in an instant. These events, although disastrous, are integral to the geological and atmospheric processes that keep the planet dynamic and habitable. The rarity of our planet, given the variety of the solar system and the apparent absence of life, raises the question, why has life emerged on Earth? The life we observe is the consequence of a series of events and factors that seem to have aligned almost perfectly to support life. And it is possible that the occurrence of these conditions is extremely rare in the universe. These are extraordinary conditions, from Earth's location in the solar system to our planet's unique physical and chemical properties. One of the first conditions is the position of the Earth in the habitable zone of the solar system. This region around the Sun is the only one in which a planet can maintain liquid water on its surface, an essential condition for life. The Earth is located at an optimal distance from the Sun, where it is neither too hot nor too cold, allowing the existence of oceans, rivers, and lakes. In addition, our planet has a protective magnetic field generated by its dynamic core of liquid iron. This magnetic field deflects charged particles from the solar wind, shielding the planet from harmful radiation and contributing to the stability of its atmosphere. The Earth's magnetic field plays a crucial role in protecting its atmosphere from being eroded into space. Without this protection, the atmosphere could gradually be lost, as is believed to have happened on Mars, leaving the planet exposed to harmful radiation. Another critical aspect is the presence of the Moon, our only natural satellite, which stabilizes the Earth's axial tilt. This stability is essential for maintaining a relatively stable and predictable climate, with seasons that contribute to the diversity of ecosystems. Without the Moon's gravitational influence, the Earth could experience drastic changes in its axial tilt, leading to extreme weather conditions. The composition of the Earth's atmosphere is another favorable condition for life. It is rich in nitrogen and oxygen, with an adequate amount of greenhouse gases such as carbon dioxide and water vapor. These gases help regulate the planet's temperature, maintaining a balance between retaining necessary heat and avoiding overheating. Additionally, Earth has experienced a series of geological and astronomical events that have been fundamental to the evolution of life. Periods of intense volcanism, collisions with asteroids, and ice ages have caused mass extinctions, but they have also opened ecological niches for the emergence of new forms of life. Earth's chemistry has also favored the complexity of life. The abundance of elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, essential for biomolecules, along with the presence of liquid water, has allowed the development of complex organic chemistry. Life on Earth has also been an active participant in modifying its own environment. Through processes such as photosynthesis, living organisms have altered the composition of the atmosphere, increasing the concentration of oxygen and allowing the development of more complex aerobic life forms. Together, these extraordinary conditions create a delicate balance that has allowed Earth to be an oasis of life in the inhospitable universe. The unlikely convergence of so many favorable factors in one place raises intriguing questions. In what other corners of the universe do these factors exist? Are all these factors necessary for life to arise? Auroras, both boreal in the northern hemisphere and austral in the southern, are one of the most beautiful natural spectacles on our planet. They originate in the solar corona, the outermost layer of the sun, where solar winds are generated, a constant flow of charged particles that travel through the solar system. During periods of intense solar activity, such as solar flares and coronal mass ejections, large amounts of these charged particles are released into space. When these particles, mainly electrons and protons, reach Earth, they interact with the Earth's magnetic field, which channels them toward the magnetic poles. As they approach the Earth's atmosphere, these energetic particles collide with atoms and molecules of gases such as oxygen and nitrogen. These collisions excite atoms and molecules, which then return to their original state, emitting small bursts of light in the process. The sum of these emissions produces the bright, colorful lights we know as auroras. The different colors of the auroras, which vary from green and pink to red and violet, depend on the type of gas with which the solar particles collide and the altitude at which these interactions occur. Oxygen, for example, produces green and reddish tones, the most common in auroras, while collisions with nitrogen can generate blues and purples. Green lights typically occur at altitudes of up to 150 kilometers, while red lights occur higher up at altitudes of up to 300 kilometers. Variations in the intensity and orientation of the Earth's magnetic field and the quantity and energy of solar particles influence the appearance and shape of auroras, which can range from a soft glow to arcs and curtains that stretch across the sky over hundreds of kilometers. Auroras are more frequent and visible in the polar regions due to the inclination of the Earth's magnetic field, which facilitates the entry of particles into these areas. But during periods of intense geomagnetic activity, they can be observed much further south or north than usual. These events, known as geomagnetic storms, can cause spectacular auroras that are visible in mid-latitudes, far from the poles. The moon, since ancient times, has been a beacon in the darkness, guiding travelers and sailors with its silver light. Its cycle, from the new moon to the full moon, has marked the passage of time for many civilizations, becoming a symbol of change. However, the influence of the moon on Earth goes beyond the cultural and symbolic. It has tangible and powerful effects on the planet. One of the most obvious impacts is its influence on the tides. The moon's gravity pulls on Earth's oceans, causing the rise and fall of sea level, known as high and low tides. This daily phenomenon affects marine life, from the creatures that inhabit intertidal zones to the extensive ecosystems of mangroves and estuaries. Eclipses are another natural spectacle that demonstrates the connection between the moon and Earth. A solar eclipse occurs when the moon passes between the Earth and the sun. casting a shadow on the Earth and briefly darkening the day. Similarly, a lunar eclipse occurs when the Earth is between the Sun and the Moon, casting the latter in the Earth's shadow. Additionally, the Moon has played a role in the evolution of life on Earth. Some scientists suggest that the tides generated by the Moon could have been crucial at the dawn of life, providing a dynamic environment that fostered biological complexity. The intertidal zones, with their constant alternation between water and air, could have been the natural laboratories where life began to experiment with the colonization of dry land. Exploration of the Moon has expanded our knowledge not only about our satellite, but also about the Earth itself. The Apollo missions marked a milestone in the history of space exploration, bringing back lunar samples that have provided invaluable information about the formation and evolution of the Moon, and, by extension, the Earth-Moon system. These lunar rocks, silent witnesses to the early days of the solar system, have helped scientists reconstruct the early history of our own planet. Mars, the red planet, today appears as an arid desert, with its surface covered in iron oxide dust, which gives it its reddish color. Despite its inhospitable appearance, Mars may have secrets hidden beneath its surface, including the possibility of having supported life in the past. It may have once had conditions similar to those on the early Earth. Exploration of Mars has revealed a diverse landscape, with huge volcanoes, vast valleys, and ancient dry riverbeds. This geography suggests that liquid water, essential for life, once flowed over its surface. Robotic missions to Mars have been instrumental in increasing our understanding of the planet. These robotic ambassadors, equipped with a variety of scientific instruments, have analyzed samples of Martian soil, studied its atmosphere, and searched for signs of past and present water. The data collected has provided evidence that Mars once possessed rivers, lakes, and even an ocean in its northern hemisphere, raising the possibility that microbial life could have existed in the past. The planet has also become the focus of ambitious future plans for human exploration and possibly colonization. Mars' tenuous atmosphere, composed primarily of carbon dioxide, along with extreme temperature conditions and low gravity, presents significant challenges for human presence. However, technological advances and research are paving the way so that, in the coming decades, astronauts will be able to set foot on Martian soil. In addition to robotic missions and manned exploration plans, Mars has captured the imagination of the public and the scientific community with the possibility of terraforming. It is an ambitious idea that involves modifying the Martian climate and atmosphere to make them more habitable for human life. It is a concept that stimulates debates about the technological capabilities and ethical responsibilities of humanity in manipulating planetary environments. The search for life on Mars, whether past or potentially present in subsurface microenvironments, remains one of the most exciting scientific goals of Martian exploration. The detection of methane in its atmosphere by missions such as ESA's Mars Express and NASA's Curiosity has fueled speculation about active biological or geological processes. Although the existence of life on Mars remains an open question, the study of this planet provides valuable lessons about the limits of habitability and the resilience of life in extreme conditions. Mount Olympus is a geological wonder, not only of Mars, but of the entire solar system, with a height of approximately 22 kilometers above the mean level of the Martian surface and a base that extends almost 600 kilometers. It is the largest volcano in the solar system. The formation of Mount Olympus is the result of billions of years of volcanic activity. Unlike terrestrial volcanoes, which are typically found at the boundaries of tectonic plates, Mount Olympus formed in a hotspot, similar to the one that created the Hawaiian Islands on Earth. Its scale far exceeds any terrestrial volcanic formation. One of the reasons behind its colossal size is Mars's low gravity, approximately 38% of Earth's gravity. A lower gravitational force allows structures to be taller without collapsing under their own weight. Additionally, Mars' crust does not move in the same way as Earth's tectonic plates. On Earth, hotspots form island chains as the tectonic plate moves over them. In contrast, the hotspot under Mount Olympus is believed to have remained relatively stationary, allowing the volcano to accumulate layers of lava for millions of years without being interrupted by the movement of the crust. Despite its large size, scientists believe that Mount Olympus may have had relatively mild eruptions. The fluid, low-viscosity basaltic lava, typical of shield volcanoes, would have flowed gently down the slopes of the volcano, creating long rivers of lava that contributed to its gradual expansion. Its last volcanic activity is estimated to have occurred a few million years ago, suggesting that the volcano may not be completely extinct. This raises questions about the geothermal potential of Mars and the implications for the past or present existence of liquid water and possibly life. The Valles Marineris is the largest canyon system in the solar system, stretching across the Martian surface. This enormous set of cracks and valleys covers about 4,000 kilometers, equivalent to a fifth of the circumference of the red planet. In some places, it reaches depths of up to 7 kilometers, with widths of up to 200 kilometers. To put it in perspective, Valles Marineris is almost 10 times longer, 7 times wider, and much deeper than Earth's Grand Canyon. One theory suggests that the canyons were formed by faulting and fracturing processes in the Martian crust, potentially related to the stress caused by the formation of the Tharsis volcanic region, located west of Valles Marineris. It is believed that the uplift and expansion of this region generated tensions in the Martian crust, giving rise to fractures that became the enormous canyons we see today. Other hypotheses for the formation of Valles Marineris include erosion caused by water or ice at some point in Martian history. Jupiter, the gas giant, stands as the colossus of the solar system. With a mostly gaseous composition, Jupiter appears as a world without a discernible solid surface. Clouds of crystallized ammonia paint stripes and swirls in its atmosphere, creating an ever-changing tapestry. This atmosphere, composed mainly of hydrogen and helium, harbors extreme climatic phenomena, whose scales and energies far exceed those on Earth. The Great Red Spot, a gigantic storm so big it could engulf Earth multiple times, is perhaps Jupiter's most iconic feature. This vortex, observed for more than 300 years, symbolizes the dynamic and violent nature of the planet. Beyond its impressive atmosphere, Jupiter is proud of its celestial court of moons, with more than 79 known satellites orbiting it. Among these, the Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610, stand out for their size and diversity. Europa, with its icy surface crisscrossed by lines and fissures, hides beneath its crust an ocean of liquid water that could contain more water than all the oceans on Earth combined. This icy world is one of the most promising places in the search for extraterrestrial life within our solar system, with the potential to present habitable conditions in the dark depths beneath its ice sheet. Ganymede, the largest moon in the solar system, is surprising for its size and for having its own magnetic field, the only satellite known to have such a characteristic. Its surface is a mosaic of dark and light regions,